Welcome to Puzzle 4 of the mojo-gpu-puzzles series. Today we're tackling 2D map, where we'll talk about how to work with two-dimensional matrices on the GPU. In this puzzle, we'll implement a kernel that adds 10 to each element of a two-dimensional square matrix. It's a simple concept, but this introduces a crucial skill for working with 2D data structures on GPUs, something you'll use constantly in image processing, neural networks, and scientific computing. By the end of this tutorial, you'll master two key concepts. First, 2D thread indexing, that's understanding how thread index.y and thread index.x map to matrix rows and columns. This is fundamental for all 2D GPU operations. Second, handling excess threads. We'll have more threads than matrix positions, so you'll learn proper bounds checking to prevent memory errors. Let's define our key terms for this puzzle. First, thread index.y and thread index.x. These are built-in GPU variables that give each thread unique coordinates within its block. The y-index maps to matrix rows, and x-index maps to columns. This convention comes from how computers historically stored matrices, row by row, top to bottom. Next is bounds checking. Since we often launch more threads than needed, we must verify that our threads' indices fall within valid matrix dimensions before accessing memory. Without this, we'd crash with out-of-bounds error. The next concept is row major layout. This is how matrices are stored in memory. All elements of row 0, then all elements of row 1, and so on. For a 2D matrix, the position at row I, column j is index I times size plus j. Finally, LayoutTensor, a high-performance mojo abstraction that handles memory layout and indexing automatically. Instead of calculating I times size plus j, you write tensor ij, and that's simpler and cleaner. Let's understand how 2D thread indexing works with a concrete example. In this puzzle, we have a 2x2 matrix, just 4 elements, but we launch a 3x3 block of threads. That's 9 threads. Why? In real GPU programming, block sizes are often fixed for performance reasons, so you might have more threads than data. Typically, block size is actually a multiple of 32, but we're using smaller sizes here for easier visualization. So a thread with y equals 0, x equals 0, maps to matrix position row 0, column 0. Thread 0, 1 maps to row 0, column 1. But look at thread 2, 2. That's trying to access row 2, column 2 in a 2x2 matrix, which doesn't exist. This is why bounds checking is critical. If row is less than size and column less than size, we can set a conditional that means that only threads within bounds do the work. Now the memory layout. In row major order, our 2x2 matrix is stored linearly in memory. 0, 1, 2, 3. For raw memory access, to get element row 1 column 0, we calculate 1 times 2 plus 0. That correctly gives us the memory index of 2. With LayoutTensor, we could just write output 1, 0, which does that calculation automatically. It's much cleaner and less error prone. Let's walk through the starter code. Open up problems, p04, p04.mojo. At the top, we import our GPU primitives. Unsafe pointer for raw memory access, thread index to get our thread's coordinates, device context to manage GPU operations, and assert equal for testing. We have some key constants. Alias size gets 2, alias blocks per grid gets 1, alias threads per block gets 3, and 3. We have a 2x2 matrix, launching one block of 3x3 threads. That's 9 threads for 4 elements. Perfect for learning bounds checking. Here is the function we need to complete. Function add 10 2D. We set row to thread index.y and column to thread index.x, and we have 2 lines to complete. This gets the thread coordinates for us. We need to add bounds checking and the actual computation. Down below in main, we allocate buffers and initialize data in a nested loop. Notice that row major indexing, I times size plus j. Then we launch the kernel and verify results. When this works, all our assertions will pass. Time to solve this puzzle. I'll show you both approaches, raw memory first, then LayoutTensor. First, the raw memory approach. Row is thread index.y, column gets thread index.x. Step 1 is bounds checking. We verify both dimensions. If row is less than size and column is less than size, this guards against those extra threads accessing invalid memory. Only threads where both row and column are less than 2 will proceed. Step 2, we calculate a flat index and perform the operation. Output row times size plus column that indexes in a row major way gets A row times size plus column plus 10. For thread 1, 0, we get 1 times 2 plus 0, that's 2. So we access index 2, add 10, and store it. That's it for raw memory. 2 lines as promised. Now let's see the same approach using LayoutTensor. Open p04 LayoutTensor.mojo. Notice the signature change. Function add10 2D outputs a layout tensor and has a single input called A, which is also a layout tensor, and size, which is an integer. Instead of raw pointers, we have layout tensor types with mu equals true for mutability, d type for data type, and layout specifying a row major 2D structure. The code for our solution is almost identical. Row is threadIndex.y, column gets threadIndex.x. If column less than size and row less than size, output row column gets A row column plus 10. The significant difference here is we're using output row column instead of output row times size plus column. This is because LayoutTensor handles the index calculation automatically. It knows the layout, knows the dimensions, and converts our 2D indices to their correct memory location. Both approaches produce identical results, same performance, same correctness, but LayoutTensor is easier to read and maintain, it's less prone to indexing errors, and it's self-documenting. The types tell you it's 2D. This is why from Puzzle 4 onward, we'll primarily use LayoutTensor for cleaner, safer GPU code. Let's verify that our solutions work. For the raw memory version, our output matches our expected output. Perfect. Each element is 10 more than its index. Our input was 0, 1, 2, 3, so our output is 10, 11, 12, 13. Now the LayoutTensor version, identical results. Both approaches work perfectly. Let's recap what we learned in Puzzle 4. 2D thread indexing. We understand how threadIndex.y maps to rows, and threadIndex.x maps to columns following the natural matrix convention. And bounds checking. We learned why we need to verify both dimensions before accessing memory, especially when we have more threads than data. We saw this approach 2 ways with both raw memory management using manual index calculations and the modern LayoutTensor approach with automatic indexing. Most important here is that you understand the underlying memory layout, row major ordering, even when you're using high-level abstractions. This knowledge is crucial as you tackle more complex 2D operations in future puzzles. Congratulations on completing Puzzle 4. You've now mastered the fundamentals of 2D GPU programming. Next up is Puzzle 5, Broadcasting, where we'll learn how to efficiently apply operations across different matrix dimensions. This is essential for neural networks and array programming. If you found this helpful, please subscribe to the channel and hit the notification bell to catch every puzzle in this series. If you got questions about 2D indexing or want to discuss optimization strategies, join our community over at the Module forums. That's forum.modular.com. The Mojo community is incredibly helpful and welcoming. Keep coding, and I'll see you in the next puzzle. Until then, happy GPU programming.